This video is going to review some of the basic things from exponential functions you should remember from last year from Algebra 2. So let's start with basically what the general form of an exponential function is. We know that the general form of an exponential function is y equals a times b to the x. We know that b, this value right here, is called our multiplier. And depending on the value of that value for b, we're going to have exponential growth or exponential decay. If our value of our multiplier is somewhere between 0 and 1, we're going to have exponential decay. Our graph is going to look something like this, where it's going down towards our horizontal asymptote. If our value for b is greater than 1, then it's going to be exponential growth. It's going to be a graph that looks like this. And this value a, where does this value of a come from? Well, this is our constant value. This is our starting value. This is going to be the value we have when x equals 0. So whenever the time equals 0, whatever the value for x is, when it's 0, that's going to be our starting value. So if we're given information about how much we start with, that's going to be our value for a. And then our multiplier, again, depending on whether you want growth or decay, is going to be a specific value. So let's look at these three examples and determine if they're exponential functions or not. Let's see. So number one, we've got y equals 3 to the x. Well, if I think about my basic general function, y equals a b to the x, we see that an exponential function has a value for a, which in this case is there, it's just 1, has a value for multiplier b, which is 3, and our variable x is going to be in the exponent. So yes, this is definitely an exponential function. When I look at number 2, I notice that y equals 4 to the second power, there's no variable for x. This can't be an exponential function. It's actually just a constant function, y equals 16. And our last example, y equals x to the 1.3, while it has an x variable in it, the exponent is a constant value as well. So in order for it to be an exponential function, the variable x, or whatever variable you're working with, needs to be in the exponent. How do we look at a table and determine if the pattern suggests that it's exponential? Well, again, what we know is true about an exponential function is we have a multiplier. So what we're doing instead of adding a constant value each time is we're multiplying by a constant value. So let's look at the differences here. In this first table, we'll call it table A. Our values for x increase by 1. So we add 1 each time. Well, what happens to our values for f of x? Well, in this case, they're definitely decreasing. But are they decreasing by a constant rate? Well, let's determine. If I want to look at the difference between 108 and 36, we've subtracted a value of 72. But if I look at the value between 36 and 12, we've only subtracted a value of 24. So it's not a constant value that we're subtracting. Is there another relationship between these values? And the answer is actually yes. If I think about the relationship between these numbers, what it looks like happening is I'm taking my value and I'm dividing it by 3. Another way of thinking about this instead of dividing by 3 is that I'm multiplying by 1/3. If you think of it in terms of a multiplier, it's easier to think of it as multiplying. The same thing happens here. I multiply by 1/3, I multiply by 1/3, and again I multiply by 1/3. Considering I'm constantly multiplying by a value of 1/3, I know that this is going to be an exponential function. If I want to write the equation of this exponential function, I would need to know two things. The a value. The a value is my starting value. What is the value for f of x when x equals 0? In this case, 12 is my a value because I can pull it right out of my chart here. The next number is our value b, which is our multiplier. We know we multiplied the values by 1/3. And in this case, since it increased by a unit of 1, it's just going to be to the x power. So our exponential function here would be y equals 12 times 1/3 of the x. Take a look at this next example and determine if it's exponential or not. Well, I can see that each time here I'm multiplying or adding 1 each time, so my x value is continually increasing. But what's happening to my g of x value? Is it being multiplied by the same value? Well, we could just look ahead here and see that to get from 5 to 10, I had to multiply by 2. But to get from 10 to 40, I have to multiply by 4. Even if I go backwards, I can tell that these values here are not constant. The value that I'm multiplying by has to be a constant value in order for it to be an exponential function. This is not an exponential function. How about this one? We see that each time our x value is going up by 2 this time. What about our f of x value? Is it being multiplied by a constant value? Well, to get from 60 to 20, I again multiplied by 1/3. And if I follow my pattern, it does indeed seem to be figuring out that each time I multiply by 1/3. So this is definitely going to be an exponential function. But what's the equation for this exponential function? Well, we know our starting value. We know that whenever x is 0, our f of x value is 60. So a is going to be 60. We also know that our multiplier, what we multiply by each time, is 1/3. But here's where this problem differs than our last example that was exponential. Notice that we increased our x value by 2. So if I just simply put the value of x as my exponent, that would say that for each 1 increment of x, we're going to be multiplying by 1/3. But it's not by increments of 1, it's by increments of 2. The way we modify that is we take our exponent and we divide it by how much we've gone up by. So in this case, my exponent is going to be x divided by 2. So that when I plug in, for example, 2, I'll find that I multiply by 1 quantity of 1/3. When I plug in 4, I'll multiply by 2 quantities of 1/3, and so forth, which follow the pattern that I have on my table. So anytime these values here are not 1, we need to make sure that we change our exponent. So we always divide by the value of what our increment is here.
Now let's take a look at an example that doesn't have a chart. Let's take a look at this example. We want to write an exponential model for an initial substance of 20 grams that has a half-life of 52 years. We know our basic equation is y equals ab to the x, where a in this case is our initial amount. Looking through our problem, we can see that we started with an initial substance of 20 grams, so our a value is going to be 20. Our multiplier. What happens to our substance over the time? Well, it says it has a half-life, which means that it's going down by 1/2. So our multiplier is simply that, 1/2. What about our exponent? We see that based on, like for example, our table, before it needed to go, in this case, in our last example, we had for every 2 it went up, but in this case it says a half-life of 52 years. This means that it takes 52 years for it to be half as much as it started with before. So when we're talking about, if we were looking at, for example, a table of values like we did before, what would happen is our x value would go up by 52 each time. So our exponent needs to reflect that as well. So our exponent is going to be x divided by 52. And this would be our equation. Let's go ahead and try an application problem that's going to be similar to the problem that you're going to do in class. This is from page 288, number 52 in your textbook. We've got some data in a table, and it says, assuming the growth is exponential, we want to know when the population of Columbus will surpass 800,000 people. And this is the data we have. Granted, it's only 2 points, but we can work with that. It tells us that it assumes it's exponential, which means that we know that the value is going to be going by a constant multiplier. So we're looking at Columbus, so we're really only concerned with this data right here. So let's write an equation. We're going to need the equation to solve this problem. So where do we start? Well, we need our starting point. We don't know time 0, but we can assign a value as time 0. If we say, for example, that we're starting at 1990, then x equals 0 would represent 1990. That being said, then our population in 1990 is going to be our starting value. So we're going to write that as our value for a. What's our multiplier? Well, all I need to do is determine what did I multiply this value by to get this value in 2000. Well, I mean, I could find an approximate decimal value, but really it's just a fraction of 711,470 divided by 632,910, which if you do on your calculator is approximately about 1.12. It's perfectly fine to leave it as a fraction. Since it's an application and we're not worried about it being too perfect, we can go ahead and use an approximation for decimal. So I'm going to say it's approximately 1.12, but keep in mind it's not going to be exact. Then we need to look at our exponent. How much time passed between our starting time and our ending time? Well, we went from 1990 to 2000, which was a difference of 10 years. So our exponent is going to be x over 10. Now, how do we solve this problem? Clearly, this is not exactly a nice, easy equation to solve for, but ideally what I'm trying to do is set y equal to 80,000 and solve this. we're really going to need the help of our graphing calculator to help us solve this, because algebraically, we haven't really talked about how to do it yet, and it's probably a little bit easier to get started by graphing. So go ahead and pull out your graphing calculator, and let's go ahead and do one of two things. First of all, I want you to graph this equation here, and then since we want to find out where it's equal to 800,000, we're going to graph, so this would be my y1, and then in y2, I'm going to graph 800,000 and find out where they intersect, because that's going to help me figure that out. So I'm going to pause and get my graphing calculator up so we can check and see if we have the same graphs. So go ahead and pause the video, and then when you've got it on your calculator, go ahead and unpause so we can see if we're in the same spot. So you can see now I've got my two equations. My y1 represents my exponential function we came up with, and our y2 represents the population that we're looking for. When I go to graph these two, clearly you can see that on a regular normal window, we're not going to be able to see anything because these values are way too large. This gives us the perfect opportunity to remember how to figure out what to set your window to, a key skill for any student. So let's go to our window. Let's think about what these variables mean. X. In my equation, X represents the time since 1990. Clearly, I don't need to go anything less than 1990, so I'm going to make my X min, be 0. And my X max, well, how many years do I think it's going to take until I get to, that population of 800,000? Well, we're almost there. In 2000, it's about a little over 700,000. So I'm going to overestimate and guess 30. You can guess 20 or 25, whatever you think it's going to be. It's better to overestimate than underestimate. If you make an underestimate, just simply change your window later. And since I'm going from 0 to 30, I'm going to count by 5s. Now let's talk about our y. Our y value represents the population at any given time. Well, I could start at 0 because I know the population won't be anything less than 0, but I really don't even need to see that part of the graph. If I think about it, my starting value is a little over 600,000. So let's go ahead and start our minimum at that value. And then our y max. Well, we know we want to find out where it's 800,000, but I don't want to be a little bit, so I can't see it. So let's go ahead and make that about 900,000. And to count from that, I don't want to count by ones. I'm probably going to count by maybe like 50,000 or so. Now let's go ahead and graph and see what we can see. Again, we're only going to see a piece of the graph, but the piece that we need to see is that intersection point, and that's why we fixed the window the way we did. Perfect. Here's our graph. The point that we're concerned with is this value right here, where our exponential function intersects the population we're looking for. How do we find that? Well, let's let our calculator do that by finding the intersection point. So second trace, intersect, enter on our first exponential curve, enter on our second population value, and you can put in a guess, or you can hit enter, and we find our value is about 20.7 years or so. So this is the value I care about right here. This tells me that approximately 20.7 years, or about 21 years if you want to go to the nearest whole year, our population is going to reach about 800,000. So think about in the context of the problem. They were asking us when will it be? And since we know X represents the year since 1990, we can do one of two things. We can either estimate and say, well, okay, it's somewhere between 20 and 21 years, and that's fine. You can round up to about 21 years. Both of those are going to give you an answer that's pretty close. So let's say we add about 21 years, so we have 1990. And we add about 21 years, so in about year 2011, and to be exact, it's somewhere between 2010 and 2011, that we'd reach our population here of 800,000. Again, we did an estimate. When we used our value for our multiplier, we did kind of round. If you wanted to be more exact, here's where your calculator would be nice, because you could actually put in the actual fraction of the population from 2000 divided by the population of 1990. But we need an approximation, and this is good enough for us. So in about 2011, or 21 years after 1990, is when our population is going to surpass 800,000.